Awesome. Well, hi, everybody. Thanks for coming. Good morning. This looks like it's going to be an awesome conference. So what I want to talk about today is a circle of ideas that I've been part of developing with a lot of other people, including Benson Farb and Tom Church, Andrew Snowden and Stephen Sam, John Wiltshire Gordon, Rohit Nagpal, Eric Ramos. I mean, a long list of people, some of whose results I probably won't name check all of those people with their results today in this talk because I want to kind of introduce the basic ideas, but I just want to emphasize that the circle of ideas I'm talking about is a very active one that a lot of people are working in and making progress every day. So the theme I want to start with is the theme of homological stability, which is something that I care about a lot, and it turns out that it's a theme that arises both in number theory and in topology, which is one reason I think it's appropriate for this conference. So to talk about homological stability, I first want to talk about homology. So for the point of view of this talk, some of you are topologists and some of you are not. But let me kind of give the simplest example possible. So when I talk about homology, of course I have in mind some like very grand, rich theories, sometimes even with the word like étale stuck in front of it. But for what I want to talk about today, actually everything that I have to say that's in any way interesting, which I hope is some of it, is even interesting for H1. And H1 is easier to talk about than homology in general. So let me sort of say what that is, and then you can just imagine every HI I write being H1, and I'm still hopefully saying something interesting. So if G is a group, by the first homology of G with coefficients in a field K, I'm just going to take the group. Homology is sort of a form of linearizing something that's nonlinear. So for a group, that sort of means if it starts life not abelian, I want to make it abelian. So I'm just going to take the abelianization of G. So that's G mod its commutator subgroup. Well, and then I have this field of coefficients. So let me just say an abelian group is a module for Z, so I'll just tensor over Z with K. But again, I think often I'll sort of be talking about Z coefficients, and then you can just imagine literally it's the thing that I start with a group and I give you its abelianization, the linearized version of the group, which I think you'll all agree is like a useful invariant of a group. One way to sort of understand something about it, even if we don't understand the whole thing. Okay. On the other hand, if M is a manifold by its first homology, I mean, I apologize to the topologists because this is a terrible definition of homology, but it's like a way to think about it. Let me just say, I'm going to mean I take its fundamental group and I'll abelianize that. And then tensor with K. So I feel like for the topologists, I should say, somebody should like leap in and complain like, what does this even mean? You didn't write a base point. Aha, but because I abelianized it, it doesn't matter. So exercise, if you don't like anything else in my talk, convince yourself that it doesn't matter that I didn't write a base point because when I abelianize, all those annoying issues go away. So this is an honestly well-defined thing without any choice of base point. So this is the way, given a group, I can identify to a vector space over K, a linear thing, given a manifold, or really any topological space, but there will only be manifolds in this talk. I can associate it to a vector space over K in a canonical way, and these are basic invariants of the groups or spaces involved. So that's homology. What is stabilization? I want to give two classical examples, which we're then going to kind of mess with a bit. So stabilization 1 arithmetic groups. So as number theorists, if we're going to be number theorists for a minute, I mean our favorite groups are the arithmetic groups, right? So let's see what this says about the arithmetic groups that we love. So let me just quote a famous old theorem of Borel, which says the following. If I compute the ith homology of the group SLNZ, and now let's say with coefficients in Q. So what I'm doing is if there's any torsion in this group, I want to ignore it for the moment. I'm just going to look at the free part. and tensor with Q to make a Q vector space. Okay, so this is a Q vector space attached to this group. And what I want you to imagine is that I is fixed and n is growing. So for instance, I could be 1, and you could be asking about the abelianization of this group. And it turns out that this actually does not depend on n as long as n is big enough relative to I. So let's say for all n bigger than 2i plus c, and I forgot what this constant is. I didn't write it down in my notes, but it's but for any fixed I, you can make n big enough, and maybe this vector space changes for a while. But then for all sufficiently large n, it's the same, and that's what we mean by stabilization. You have a sequence of spaces or a sequence of groups, and the homology somehow maybe changes for a while, but then it just locks into one thing and stays the same forever. So for instance, and here's another exercise you can do if you want. So e.g. h1 of SLN z q. So I'm telling you that this vector space has a certain dimension that's the same for all sufficiently large n, and I'll tell you what it is. It's 0. And this is true for all n bigger than or equal to 2. So that's an exercise. That's another exercise that you can do. Actually, it's an interesting question. I don't know how hard this exercise is for large n. But for SL2, it's a good exercise in multiplying matrices. So in other words, to say that when you tensor with Q you get 0, you're saying that the abelianization of SLNZ is torsion for all n bigger than or equal to 2. So at least for a theorem like this, I think there's kind of a pessimistic view and an optimistic view. I think the pessimistic view is just that homology is not that good of an invariant, and it's not really seeing what's going on with these groups. Because these groups are definitely not like staying the same as n gets large, right? They get like bigger and more complicated. And the homology is just always staying the same for all n. The optimistic view is that we sort of should have faith that homology is like an incredibly important invariant, that a lot of the stuff we're interested in keeping track of is seen by homology. So that should say that the fact that these groups superficially appear to get more complicated is maybe, at least part of that is an illusion, and maybe certain important aspects of them really do stay the same. So I guess because I like to prove theorems about stability, I'm going to take the optimistic view. And consider it not like a strike against homology. By the way, in fact, this holds for, I'm actually going to use this, so let me say it. In fact, this same theorem holds for any k. Okay, so that's example 1 of homological stability. Example 2, that's the number theory example. Now I want to give a topology example and talk about configuration spaces. So stabilization 2 okay, ready? So X is a topological space, and for me it's always going to be a manifold. In fact, I think everywhere in this talk it's actually going to like literally be a disk. So for the topologist, it may be like, what the hell is there to say about the topology of a disk, a contractible space? Okay, amazingly, I'm going to say something about it. So, so the configuration space, conf nx, it's the following. I would call this a moduli space. It's the space of unordered n-tuples x1 through xn of distinct points on x. So somehow all the interest in this space is in this word distinct. So I'm looking at the moduli space of sets of n points in the space which are not allowed to collide with one another. So now, just like over here I had a sequence of groups indexed by little n, here I have a sequence of spaces indexed by little n. And once again, we're going to see that there's an amazing theorem of homological stability. So let's try to understand this. So e.g., my favorite example, I'm going to take x to be, well, because I'm an algebraist, I'm going to call it the complex plane, but you could also call it the disk. So what is this space? So then conf nc, I can think of it as, so a point in this space, you should think of as some configuration of distinct points, like this is a point of conf 4 of C. I'm going to call this the space, again, betraying that I'm really an algebraist, I'm going to call it the space of square-free polynomials. This is how I usually think of it. Why? Just because if I have some set of points in the complex numbers, now I can't call them x anymore, they're complex numbers, so they have to be z. So a set of complex numbers, z1 through zn, I can associate that with the polynomial z minus 1, z1, z minus zn. So maybe I should say monic square-free polynomials. Because the condition that these guys be distinct is exactly the condition that this polynomial be square-free. It has no repeated roots. And of course, given a monic square-free polynomial, I can just compute its roots. C has the good taste to be algebraically closed, so I can do this. And so this gives me a bijection. I guess I already wrote this as a squiggly arrow, so it's hard to write the bijection symbol atop it. But there it is. Like that's a bijection of things. So the question is, what's the cohomology of this space? How does it behave as n grows? Well, I'm not going to tell you how to do this, although I am going to tell you the answer. But let's talk about H1 a little bit more. Remember, H1, I defined it as coming from the abelianization of the fundamental group. So what's the fundamental group of this space? OK? I got to draw loops in this space, right? That's how I make the fundamental group. So what is pi1 comp nc? Well, I've got to think about loops in this space. And if you've never thought about this before, it's a little complicated because the space itself, its points are sets of points in another space. This is kind of moduli philosophy that takes some getting used to, but is incredibly powerful. So let's draw a loop. A loop in comp nc, well, I'm going to think of it like this. Each point in comp nc is some configuration like I drew upstairs. And I drew it in this kind of Google Street View 3D way because I'm going to imagine we're sort of looking almost flat at it, and our loop is going to move in time, right? We're going to move from this point to another point. Well, it's a loop, so not from this point to another point, from this point to the same point. And then we imagine this loop like a little movie, right? As time goes upward on the board, our points are moving. So they're just kind of going. This guy's going to kind of go around to wherever it goes. Remember, it doesn't have to end up at the same point, right? Because it's this set of points has to be preserved, but they're not. This is an unordered set. So this guy has to end up somewhere else. And now all the fun comes right here because there's only one rule for configuration space. The rule is the points are never allowed to coincide. So at every time slice, the points have to be all distinct. And what that means is that these strands cannot cross. So it's got to either go in front or go behind. Let's draw it behind. Maybe it ends up there. And then something happens over here. And something happens over here. OK, so what did I draw? I drew a braid. So I mean, I have to sort of stop for a moment and say, I mean, I didn't even know who else was coming or what people were going to talk about. But of course, I should have realized that if you're going to have a conference about algebra and geometry and topology, I mean, what are you going to talk about besides braids, right? I mean, that's somehow where they all meet. And I literally think that all four of us are talking about braids. Saj, are you going to literally say the word braid in your talk? Yeah, OK. And Alan, you're at least going to say mapping class group, right? Link, OK. So I mean, you know, a link is just like when two ends of a braid love each other very much. I mean, that's, so yeah, it's no coincidence. I mean, I sort of got into braids very late in my mathematical education, but I have to say they're sort of in some sense like the arithmetic groups, and I think maybe Alan's going to talk about sort of some interesting analogies between the context of arithmetic groups and the context of the braid group. I mean, they seem to be incredibly central in touching on things that I care about as a number theorist, which is, I mean, I got into this from like thinking about like the Cohen-Leinster conjecture and ideal class groups. So that's another story I won't tell today. To topology, to geometry, to like, you know, exotic realms of like representation theory and just everything. So anyway, here the braid group will manifest in this talk as the fundamental group of a certain of this moduli space, this configuration space. And so, of course, concatenating two loops is just stacking one braid on top of the other. So this is the braid group of R10. And so pi1 of comp NC is just Arden's braid group on n strands. And so, well, I'm going to write H1, but it turns out that this space is what's called an Eilenberg-MacLane space, a K pi1, which means that not only its first homology, but actually all of its homology is the homology of the braid group. So I'll just write HI comp NC. So this problem that in one sense is about topology is in fact a question about the cohomology of this very interesting discrete group, which by the way, I mean, you can write down an explicit presentation for it. It's like very well understood. You can read about it in Joan Berman's beautiful book or in Benson Farb and Dan Margolit's kind of even more up-to-date book about the mapping class group. But the good thing is that this is really known by an amazing theorem of Arnold. So ready? So here we go. Oh no, I want to say before I pull aside the curtain on Arnold's theorem, let's compute this for n equals 1 and 2. Okay? So what is this? Okay, n equals 1 is pretty easy. It's the configuration space of one point in the complex plane. Well, that is the complex plane. So so I guess the cohomology is entirely supported in H0, right? So dim H0 equals 1, all else 0. What about n equals 2? Well, let's think what's going on. I fix the first point. That's a contractible choice, right? It can be anywhere in C. The second point can be anywhere in C except that first point. So it sort of has a punctured complex plane, which is to say a circle of places that it can be. Now I sort of cheated because this is supposed to be unordered, so I have to mod out by something. But maybe I'll just tell you again as an exercise that conf NC is actually homotopic to a circle. So dim H0 equals 1, dim H1 equals 1, and all the other cohomology groups vanish. Already for n equals 3, it's a little bit harder to see what's going on. Like, I mean, I think it's hard to draw a picture of that space and to have a picture of what its homology is, but I'm going to tell you. So theorem of Arnold in the 70s, and this is kind of, I think, the work of Arnold and of Graham-Siegel really sort of starts the whole industry of homological stability and topology, I think, is that the dimension of HI of comp NC is the dimension of H0 equals 1 for all n. Oh, sorry, I'm doing lower. The dimension of H1 is 1 for all n bigger than or equal to 1. And the dimension of HI is always 0 for all n. So this is an immensely strong stability theorem. What it tells you, I mean, what does it say for like n equals like 100, right? I take the cohomology of the braid group on 100 strands, which is a pretty complicated group. Oh, and I better say, I have to say something immensely important, that this is with rational coefficients. So if I didn't say that, if I said it with z coefficients, it would still be stable, but it would actually be pretty complicated to write down what it was. So for the moment, I talk about rational coefficients. That's why I can only That's why I can get away with just telling you the dimension of the group, right? It's a Q vector space, so all there is to say about it is its dimension. So here's what I'm saying. If I say the braid group on 100 strands, it's rational cohomology. It has one dimension of H0 and one dimension of H1. In other words, the space looks like a circle. From the point of view of rational homology, it's a point, then it's a circle, and then it's a circle forever. So this is another example that is in some sense very similar to what we saw in Borel's theorem, that these groups do in fact get more and more complicated, but from the point of view of rational cohomology, they stay exactly the same after n equals 2. And again, the reason I came to this is because in number theory, this has all kinds of interesting applications when you sort of start to replace homology with atomic cohomology and count points on moduli basis over finite fields, et cetera, et cetera. A lot of regularities that we are used to expecting in number theory are in some sense explained by these kinds of homological stability theorems. But what I want to talk about today is actually, now that I've sort of given you all the good news about stability, I want to kind of mess with you a little bit and talk about instability. So now I'm going to go back to these two examples. So let's come over here to the arithmetic group side of the board and say, so apparent instability 1. So here is arithmetic groups. So here's one remarkable thing about Borel's theorem, is that what he's really doing is showing you that the cohomology of that arithmetic lattice, SLNZ, essentially it's all coming from a kind of cohomology computed on the ambient Lie group SLNR. And he's really showing the stability there. So given that that's true, I mean, one lattice embedded in SLNR is very much like another. So it actually also applies to any finite index subgroup. So in particular, here's the finite index subgroups I want to talk about. Again, as a number theorist, the ones we like are the congruent subgroups. So let me remind you what that is. I'm going to define. So let's fix P for all time. P is some prime. And I'm going to define gamma n of P is going to be the kernel of the map from SLNZ to SLN Z mod PZ. So this map is just I take a matrix with integral entries and I reduce all the entries mod P. And this map is surjective. That's actually not completely obvious. It's worth thinking about why that's not obvious. It's a fact called strong approximation. And its kernel is a group called the congruent subgroup of level P. So it's matrices congruent to the identity mod P. So Borel certainly shows that the HI of gamma NP with rational coefficients is stable as n grows. As always, n is growing with I fixed. So this group is just exactly the same as SLNZ from this point of view. But something very different happens when we study this with mod P coefficients. And we do actually want to do this, right? I mean, the cohomology of arithmetic groups with all kinds of coefficients is something that arises quite naturally. And let me show you what goes wrong. But what about HI of gamma NP with FP coefficients? And of course, P equals P. That's why we're in a situation of grave danger. Well, once again, I'm going to hold to my idea that I'm going to write HI, but we're going to pretend we're talking about H1 because we can already see the issues there. So H1 is given by, OK, I'm going to slightly go from a space to its dual for those who are annoyed about things like that. But Well, no, I think I'll say it this way. Okay, so what we need to compute is what is the abelianization of this group. Remember, the abelianization of SLNZ, I told you, was a torsion group, and in fact stabilizes. But what's the abelianization of this group? It's actually not so easy to compute, but I can at least tell you a chunk of it. So what is this? Because this group has a very natural abelian quotient. Namely, I can pick the following. I can get gamma n of p and map it. I can certainly quotient by the group of matrices which are congruent to 1 mod p squared. And then the miracle is that this group is abelian. I don't know how many of you guys have done a computation like this before, so if you haven't seen it, it's like a little bit weird because this is some kind of like group of n by n matrices, which is highly non-abelian. You're modding it out by some finite index subgroup. Why is this abelian? Because if A and B are congruent to 1 mod p, so 1 means the identity matrix, then their commutator is 1 mod p squared. So again, an exercise this is just an exercise in multiplying matrices together, which I highly recommend. And so that means that in particular, if I mod out by all matrices that are congruent to 1 mod p squared, I get an abelian group. Okay, so what is this group? Well, it's pretty big, right? Because I mean, think about what I'm doing here. I mean, each entry, I know it's 1 mod p, and I'm modding out by the entries where it's 1 mod p squared. So roughly speaking, I'm going to get actually n squared copies of z mod pz. Not quite, because I said SL instead of GL. And that kills one of them. So it turns out that this is isomorphic to z mod pz to the n squared minus 1. A better way to say it is that it's isomorphic to the space of trace 0 matrices over FP. So now, are there some representation theorists in the room? I feel like you guys are a very diverse group. So why, if I was talking about SLN, and then suddenly I'm talking about the space of trace 0 matrices, n by n matrices, like what did I do? Yeah, it's the Lie algebra, right? Okay, so for the p-adic fans, what's really going on here is that moving things to be more and more congruent to 1 mod p is in the p-adic topology, moving them closer and closer to the identity. And as you guys know, a sort of very small neighborhood of the identity in a Lie group is like its Lie algebra. And more or less that's what I'm doing here, and that's why this thing pops up. If I could write those German letters, I would write like little SL n here, but I don't know how to write those. Okay. But the important thing about this, I mean, I'm not going to tell this whole story about Lie algebras. I just want to comment that whatever this is, it's definitely not stabilizing in n. Right? I mean, as n gets bigger, this gets bigger. So it's totally not like this Borel story that I told you. This grows with n. But you'll note that, of course, if I tensored with Q, it wouldn't, right? I mean, it's a torsion group. In fact, if I tensored with any field whose characteristic was not P, we wouldn't see this pathology, but here we do see it. So here's the instability. Okay. Let me do one more instability. Apparent instability 2. The pure braid group. So what is this? It's just like I replaced the SLNZ with a natural finite index subgroup. I'm going to do the same for the braid group. I told you that we were studying sets of unordered configurations. But of course, it's also natural to study the set of ordered configurations. So let me define pconf for pure configurations, n of x, is now just the ordered n-tuples of distinct points. And this has a very, actually it has an even simpler description. I can just say, well, it's x to the n is all the ordered n-tuples, and then I just subtract out all the diagonals. So over each pair I and j of indices, I subtract out the locus where xi equals xj. And what we're going to see is that here, even the cohomology of the rational coefficients gets screwed up and appears to be unstable. So let me put this one up and then pull these guys down so we can see this. So e.g., when x is c, p conf n c is just, it's c to the n minus the union over all I and j of the locus where zi equals zj, which if you like is a hyperplane, right? It's like a codimension 1 linear subspace of C. Okay, so what did I do? I took a vector space over C and I removed a bunch of hyperplanes. That's called a hyperplane complement for obvious reasons. And these spaces have like an immensely beautiful topology, and it was all worked out. I always have to say by like two guys at Wisconsin, like Orlick and Solomon. So if you've heard their names, that was like a Wisconsin product from before the time that I was there. But in particular, and by Orlick Solomon technology, you can actually work out all the homology of this space. But let's stick to just doing H1. The H1 of a hyperplane complement is just, it's easy to describe what it is. It's just generated by the hyperplanes. I mean, right, if I had, C to the n is contractible, so there's nothing. And each hyperplane I strike out gives me a new class in H1, which is basically like a little loop around that hyperplane. So H1 of P conf C with coefficients in Q is the space spanned by hyperplanes, and well, there's n choose 2 of these, right? I mean, here they are. I guess I should have said that obviously this is for unordered pairs I and j, right? It's the same to say zi equals zj and zj equals zi. So this is isomorphic to q to the n choose 2, or if I wanted to sort of make this more canonical, I would say is space spanned by unordered pairs drawn from the set 1 through n. But again, from the point of view of stability, the important thing is that this is a total fail because this obviously grows with n. Unlike the braid group, even the first homology of this space is growing with n. So again, grows with n. Okay, so thesis, antithesis, synthesis, right? I told you about stability. I told you about instability. Now I need to reveal why this apparent instability is actually stability. So let's look at these two examples, and then I'll close by like talking a little bit about the definition of an FI module and sort of how we wrote down this definition in order to sort of get a handle on in what sense these guys were really stable, even though they looked not. So maybe I'll make a nice fresh board and write these two examples again. So space of trace 0 n by n matrices over FP, and space spanned by, maybe I'll say this one is over the rational numbers, spanned by unordered pairs of integers between 1 and n. So these are two, each one of these is a sequence of vector spaces whose dimension grows with n. But what I want to remind you is that these spaces are not just vector spaces. They are representations. They carry natural group actions. And if God gives you a representation, you've got to use the representation. Right? I mean, it's horrible to kind of strip it of its clothing and treat it like a naked vector space. It's a representation of what? Well, this guy's a representation of the symmetric group on n letters. Right? That's what naturally acts. And I'll emphasize that it acts on this homology because it acts in the space, right? I mean, if I have an ordered n-tuple, and they're all distinct, I can permute them, and it's still distinct. So I'll remind you that this whole space carries an action of the symmetric group, and the quotient by that action is just the space we studied before. Now this guy, again, the representation theorists know Lie algebra carries an adjoint action of the Lie group. So I could say, OK, this guy carries an action of GLNFP. Maybe I will write that. I guess should I say PGLNFP? But now, actually, I am going to cheat. Because in here, there's certainly also a symmetric group, right? The permutation matrices. So when we first started working on this, we didn't really know how to kind of promote this whole theory I'm talking about to the GLNFP story. Now that is worked out by Snowden and Sam and Putman, and just in the last year or so. But I'm going to sort of talk about rendition 1 of this theory, which just has to do with representations of the symmetric group. So if you like, I'm going to do this whole talk is like over the field of one element. So nobody liked my field with one element joke? OK, it's OK, the point is that both of these things carry actions of a group. And now I want to say something weird. Like, let me do it for this case. So as n changes, what I want to say is that this is the same representation. But of a different group. I mean, n is growing, and so it's a different symmetric group, but it's always the representation on the unordered pairs. So this, somehow we can see that somehow it's always the same thing, even though n is changing. The only problem is that, of course, this makes no sense. I mean, the representations of a group are what they are. So the question is, what do we mean? What could we mean? What should we mean by saying that as n grows, this thing is always the same representation, even though it's of a different group? And the same thing here, by the way. I mean, I would say that this n squared minus 1 dimensional representation of Sn is also the same for each n, even though it's a different group. So there's a couple things we could mean by that. And we sort of actually, there was some churn over the years as we sort of messed with different ideas about it. And I'll sort of tell you where we came to. So this is really the closing part of the talk. What could this mean, and like what kind of stability is actually taking place here? So let me first say, I think the first thing you might think of, especially the representation theorists in the room, which kind of works. So one thing you could do is, if you have a representation of the symmetric group with rational numbers, you can break it up into irreducibles. And we know that the irreducibles are indexed by partitions. OK? So one idea break rep up into irreducibles. Yes. I could also write a little better looking at this again. Better and larger. Let me draw the partitions. How about that? I'm going to draw a picture. So for instance, actually for some reason in my notes I wrote down H2 rather than H1. So So e.g., if I write down the H2 of pconf and C as a rep of Sn, you actually see an amazing kind of stability, which is this. Okay, let me try to draw this. If I break this up into irreducibles, it's 2 copies of this. Okay, now what does this mean with the little dot, dot, dots? What it means is this is supposed to be a representation of Sn, right? So when I draw the little dots here, I mean this bar is really long. How long? Well, there's only one box here, and there's got to be n boxes in the partition, so this is length n minus 1. So some people call this a padded partition. And now let me write it out. It's plus twice plus 2 copies of this. So now the long bar is n minus 2 plus 2 copies of this plus 2 copies of this plus 1 copy of this plus 1 copy of this, and this is for all n bigger than or equal to 7. So it's, I can tell you it's actually quite satisfying to like see your computer make these. And you don't see it, you have to let n be pretty big and do a lot of computation before you see it. I mean, I'll point out that you have to let n be at least 7 because if n is 6, look at this guy here, right? There's sort of 4 boxes here. So you better have at least 3 boxes in this top row or else it's not a legit partition, right? So you can't even write this down until n equals 7. But then once you do, it looks like this. So this is certainly one picture of what it might mean to say, I have the same representation again and again and again. This top bar is just getting longer and longer. So this is one way to describe what's going on, but it's unsatisfactory in certain ways, at least, and I think chief among them is that this story definitely does not work in characteristic P. Right? If any of you know about the representation theory of finite groups, including symmetric groups in characteristic P, you know that it's like very terrifying and a complete nightmare. And in particular, the category is not semi-simple. You can't break things up into irreducibles. You can't draw partitions. You can't do anything. I don't know. Some people can do something, but not me. So this was kind of the version of the theory that was called by Benson and Tom in their original paper on this, representation stability. I want to kind of, let me talk about a different sort of more category theory flavored way of thinking about how to address this question. Maybe I'll comment again for the fans of classical representation theory of Sn. If I look at this guy and say like, okay, this corresponds to some representation of Sn for each n. What's its dimension? Like there's a formula for this, and it's not hard to check by pure thought that the dimension of this is always a polynomial in n, at least for n large enough. And the degree of the polynomial, this is cool, is like the number of boxes below the top row. So you can just kind of read off that like, okay, the dimension of this whole thing as a function of n is like some polynomial that's linear, quadratic, quadratic, cubic, cubic, and then this is like the leading term of this decomposition. And so indeed, for instance, the dimension of this cohomology is, at least for n large enough, a polynomial in n. And so one of the things we were investigating was this fact that dimensions seem to always be eventually polynomial in cases like this. And of course, that statement makes sense over Fp just as well as it does over Q, even though we can't draw partitions. So one thing we were trying to do was capture that intuition. So how to make this work more generally? Let's see how long I have. Perfect. OK, we're good. So let me go back to this story of the p-comps. We have a sequence of spaces, right? We have p-comp 1, C, this simple guy, which is just C, the braid group on one strand. And actually, what I'm going to say right now has nothing to do with C, so I'm just going to write, you can imagine whatever space you want here. And what I observed is that each of these spaces has an action of a symmetric group on it, right? So like S3 acts here, for instance, and on this one, S4 acts. But those are not the only maps in this diagram. There are others, not just self-maps, but maps between these different spaces. Really? How do I do that? OK, I will tell you. So how do I get a map from here to here? OK, so I'm given 3 distinct points in the space. I'm sorry, I'm given 4 distinct points in the space, and I want to have 3 distinct points. How can I do that? It's easy. I just forget one of the points. Wait, which point? Good question. OK, I can fix that. I mean, they're ordered, so I can say forget the first point. That's one map. Forget the second point. That's a different map, et cetera, et cetera. OK? And then so these maps, an arrow to the arrows, is forget points. OK, so there's one, in terms of convenience of exposition, I'm going to do something terrible, and now, just for the last 10 minutes, talk about cohomology instead of homology. Is that OK? I really have no choice, so I hope it's OK. OK. So in fact, there are maps the other way too, but I don't want to talk about them. That's why I'm going to use these maps that are this way. So what this means is that, so in fact, for any injection from the set of integers up to m to the set of integers up to n, we get a map from p conf n down to p conf m, which just sends x1 through xn to x phi of 1 through x phi of m. And because this phi was an injection, right, none of these points are the same. So I mean, if the two are just next to each other, then there's not so many injections. There's only n of them. But I mean, if they're farther apart, there's like really a lot of maps. So this is a very rich structure, much richer than just having this group action on each thing. And so if we want to be category theorists about it, what we would say is this. We would say, let's let Fi be the category whose objects are finite sets and whose morphisms are injections. Then pconf is a contravariant functor from Fi to topological spaces. Contravariant because notice that the map on sets went from m to n, and the map on spaces went the other way. Well, if I don't like contravariants, I can repair that by applying cohomology, which is also a contravariant functor. That's why I need to say cohomology for the moment. So hi of pconf is an honest covariant functor from Fi to, and with whatever coefficients, to k vector spaces. And this kind of functor is what's called an Fi module. So this is my definition. So this is studying the category of Fi modules. Again, I don't know how categorified you guys are, but like, this is somehow just a dressed up version of doing representation theory. As you guys know, a group is just a category with one object. Right? So when we study representation theory, we're studying functors from that category to the category of vector spaces. This category is, well, it doesn't have one object, but it just has like a sort of, there's not that many finite sets, right? It's a pretty small list of objects. And so when we study the category of FI modules, what we're really doing is studying the representation theory of this category. And you see that this category has within it, so notice that what I want to say is that this category sort of has all the symmetric groups kind of inside of it. So I'll just note that if V is an FI module, we can think of this as, okay, so let's be careful. For each object of FI, you get a vector space. The objects are just finite sets. So I can think of this as a sequence, V0, V1, V2, V3, where what I mean by V sub 3 is the functor applied to the set 1, 2, 3. And now what structure, if I sort of forget the whole category and just think about V3, any morphism from this set to itself in Fi, by functoriality, has to give me a map from this vector space to itself. So what are the injections from a finite set to itself? Just permutations, right? So here, S3 acts, and so here, S3 has to act. And you get the same picture, except the arrows are the other way. So the point is, a module for this category just is a sequence of vector spaces, one for each n, the nth one being a representation of Sn, with these maps between them. So it exactly captures the structure that we saw. And if you're careful, you can see that this structure is possessed both by this configuration space case and this congruent subgroup case. And then what it all comes down to is that, so I'm not really going to state so many theorems very precisely in this talk, but I'll say the main idea is that, so everything we care about in representation stability, let's say dimension being eventually a polynomial, the character of Sn being stable in some sense, is equivalent to V is finitely generated. So in any module category, you have a notion of what it means to be finitely generated. And this point of view actually was incredibly useful because, for instance, I'll give an example. One thing I think that was hard to understand from the point of view of drawing partitions. First of all, that didn't even work over FP. Second of all, it was hard to check things like, well, what if I have two representations like this and I tensor them? Does it still have the same property? That's kind of messy. On the other hand, the fact that the tensor product of two finitely generated things is again finitely generated is completely trivial. So from this point of view, it makes a lot of things that seemed hard look much easier. On the other hand, there was something that, to make this all go through, to make this apply to the cases in topology and number theory that we're interested in, something that I think of as easy was actually hard. So I'll tell you what it is. So the key technical point, after all, this is easy to say, but how do I know that the Fi module that comes from a configuration space, how do I know that actually is finitely generated? It can be hard to prove that things are finitely generated, right? So the key technical point, I'm writing small and badly again, sorry. I'll just say that this category of Fi modules is Noetherian. What does that mean? It means that a subobject of finitely generated is finitely generated. So if you're used to commutative algebra like I am, like I'm an algebraic geometer, you just think of this as something you learn in Matsumura or something when you're a young grad student, and then you sort of read the proof once, and then you sort of just accept it as a fact of life, right? I literally never for 1 second thought I would ever try to prove anything was Noetherian, because I'm just that's just how things are. I work with polynomial rings. In algebraic geometry, we don't work with non-Noetherian rings. That's just a pathology. So it was somewhat sobering to realize that in this case, just to have arguments that we're used to doing in commutative algebra work, you definitely need this. There's a reason whoever wanted to prove this. It's important. And it's really not so obvious in this case how to prove it. So in some sense, like the hardest part of our work writing this paper, this is the paper of myself and Benson and Tom that introduced this definition, was proving that this category is Noetherian. Now it turns out that we proved it totally the wrong way. So we proved a version of it in that paper in characteristic 0. Then my grad student Rohit Nagpal figured out a much better proof that worked in all characteristics, and in fact over an arbitrary Noetherian ring, which we wrote up in a second paper with him. And then I think Steve and Sam, and together with Andrew Snowden, has an even better proof that works for a wide variety of categories sort of this flavor. And sort of now we see, we didn't know this, but sort of now it's sort of clear from the work of Snowden and Sam that there's sort of some huge spray of categories which are somehow Fi-like, of which Fi is the simplest one. This is a theory that's called modules for twisted commutative algebras. And there's quite general Noetherian results, which somehow seem to be at the bottom of everything. So for instance, Andrew and Stephen's paper proving this Schwartz conjecture, which just was a big deal and there was a board by key talk about it, is essentially proving Noetherianness for the version of this category where instead of symmetric groups everywhere, I write like GLNFP everywhere. This was a category we tried to understand but couldn't figure out how to do anything with it, and they kind of really wrote down the right definition, proved it was Noetherian, and everything. So this is sort of, I mean, somehow it's quite cool. I mean, I think we're at the beginning of a subject that we don't really know the shape of yet. It's definitely a kind of representation theory. But it's not the representation theory of classical groups or of symmetric groups. It's a representation theory of these categories which somehow are infinite sequences of these groups strung together, which seem to have examples just coming up all over the place in algebra and geometry and topology. So I'll stop there. Thank you guys so much. Yeah.
I like to think about C as P1 without 1 point.
Me too.
So what if I replace P1 by a genus G surface? Is the story becomes very complicated?
Megan's going to tell us about it, right, Megan? I don't know exactly what you're going to say. Megan McGuire, who's a student at Wisconsin, but not my student, Melanie's student, is going to talk about configuration spaces of points on genus G surfaces, I think. But you're going to say some unstable stuff, right? Some authentically unstable stuff, not like the apparently unstable, but the actually unstable. But yes, the point is that I didn't really, I wanted to kind of give like 80% motivation and 20% fact in this talk. So like, I'll just say that in the paper, the stuff I said about conf n C, it holds for conf n of an arbitrary manifold. And it's essentially the key technical engine is this result of Burt-Totaro, which basically gives you a spectral sequence that converges to the cohomology of that configuration space. And shows that in some sense, the cohomology of configuration space of a manifold all comes from either the cohomology of the manifold itself, or like, I mean, imagine your endpoints like all coming together like really near each other on a manifold. Okay, what makes a manifold? That when you do that, you're basically in Euclidean space. And you can just forget about the rest of the manifold. So Totaro shows you how to sort of essentially stitch together the cohomology of the configuration space from configuration spaces of Euclidean space, which is like local stuff, all the points nearby each other, and the global cohomology of the manifold. But when I say stitch together, I mean look at the convergence of some spectral sequence, which I don't really know anything about how to compute the differentials of. And that's why you need like very general theorems like Noetherianness, where you just say like, I don't care what any of the maps are in that spectral sequence are. I just care if the first page everything is finally generated, then forever everything is finally generated. And that's what we use. So it's very soft in some sense. Yeah?
So what type of twisted commutative rings pop up?
So okay. This is a theory. By the way, I'm glad you asked that because I slightly misstated. The way I said it, I made it sound like Stephen, Sam, and Andrew Snowden invented the idea of twisted commutative algebra, which is not true. This is like an old thing that exists in literature, but that I think is super interesting and like people, to be honest, completely failed to pay attention to. And we only found out about it after the fact. So I'm not going to give this whole definition, but it's a twisted commutative algebra is a certain kind of graded algebra, and a module for it is some kind of thing. Okay, that really says nothing. Let me just say that it turns out that the very simplest twisted commutative algebra there is basically just one-dimensional in every degree. And modules for that, it turns out, and again, this definition existed in the literature before us. It turns out that that is the same as an FI module. So we're calling it an FI module, but it existed in this theory of twisted commutative algebra before. Although the properties of it that we proved, those weren't in the literature, but the definition actually did exist. So I mean, I think what Stephen and Andrew are doing is developing a much more general theory of modules for twisted commutative algebras and understanding sort of what is like and unlike standard commutative algebra in this theory. And it's developing as we speak. Yeah, Joseph.
In that H2 example, you had like stability as soon as it was possible for the final answer to be like what the representation was. Is that something that you tend to see generally in these examples?
It's actually a bit, so in the paper we give some bound on where stability kicks in. That's actually also something that, thanks to Stephen and Andrew's work, is like much better understood now than it was in our original paper. And actually there, I should say, actually the guy who understands it best is Eric Ramos, my student who's graduating next year. So it turns out that, so you guys know, like, okay, algebraic geometers in the room. If something is like eventually a polynomial, but not for the first few n, what's like that you know? The Hilbert function, right? Of like, like you take some ideal in a ring and you like look at what's its dimension in given degree, and the Hilbert polynomial, Hilbert's theorem says this is eventually a polynomial. And then you like learn that in algebraic geometry, and then, okay, you're like, that's cool. But then when you grow up and you're like, wait, why isn't it a polynomial all the time? You learn that the obstruction is like some kind of Tor. There's some kind of homological algebra story. And those things are what's keeping it from being polynomial in the small range. So now, not in our paper, but with Eric's stuff and with Andrew and Stephen's stuff, there's a very similar story where the obstructions to this thing being the thing that it should be for large n are all expressed by certain Tor groups in the category, and essentially figuring out what the stable range is figuring out where those Tor groups die, like what's the maximal degree of them. So it's some kind of homological algebra thing in this context. Holly, did you have a question?
Yeah, does this kind of stability also exist for general mapping class groups, say the surfaces of the mapping? And also, what acts there?
Yeah, okay, so here's that's a great question. So Ellie asks about, Ellie is like topology shaming me and reminding me that a braid group is just like a slight example of like a mapping class group, which is, no, but this is great because, okay, so here's the story. If I fix the genus and let the number of points grow, so I look at the mapping class group of say Gn with n growing, this was worked out by, I should have said her name. Oh my God, I'm sorry, I'm blanking. No, Benson's student who was a postdoc at Northeastern and is now at Autonoma. Oh my God, I'm really embarrassed. Rita Jimenez. Okay, so Rita Jimenez worked this out in her thesis, and everything is true for a fixed genus and large n. Now for growing genus, it's an interesting story. I mean, as we know, the stability of the cohomology for the mapping class group, let's say with n equals 0, no punctures, and g growing, that's harder than what Arnold did. That's what Harrer proved in the 80s. You can do something, but I think a very interesting question would be like, so here's a question that I think is not very well understood. I took SLNZ. There's a theorem of stability that exists, and you say now look at a congruent subgroup. Here's what somebody like Benson would say. He would say, okay, take mapping class group of genus G. We know the stability by Harrer. What subgroup you take? You take the Torelli group. Look at the subgroup that acts trivially in homology. That's a representation of sp2gz. And then ask, is that in some sense stable as G grows? And that actually we really don't know how to do. So I mean, I told you that thanks to Stephen and Andrew, there's a version of this story that makes sense where instead of the symmetric group on n letters, I have GLNFP for a finite field. But certainly their Noetherian result, as written, is like literally false if instead of GLNFP you have like an arithmetic group over Z, like for instance sp2gz. Something's got to be true. There's got to be some sense in which there is some flavor of stability that can be said. But at this point, I think we just don't have the apparatus. We don't even know what statement to try to prove. I think that's like a big open question.
No more questions, and then let's go off to the
Thanks.